To make things a bit more tricky, a bit more complicated, there's also some reactions that are not only temperature dependent, but they're also pressure dependent. We call these pressure dependent reactions. So sometimes the rate expression depends both on temperature and pressure, meaning this K, which is typically Arrhenius based, also becomes a function of pressure. And the two cases are, we have what we call unimolecular recombination or fall-off reactions. The rates of these reactions can increase with pressure. I'll show you how that's dealt with. And then also we can have what we call chemically activated bimolecular reactions. And these reactions, the rates can decrease as pressure increases. And now just coming back to these general formalism. So if we have this kind of three-body reaction, which we saw was there in the hydrogen-oxygen mechanism. So again, this H plus O2, this should be H, not H2, H, okay, plus O2 plus M. M is a way to denote the total pressure of the system. I'll show you what it means. Yeah, it goes to form HO2 plus M. So this is a reaction that is when you write this kind of reaction in your so-called mechanism, your code will actually solve the progress of reaction and the production rate in a different way. And what happens is a Q that reaction progress now becomes a function of, for every reaction K goes to K, you have AKI, which is a factor which tells us how dependent a reaction is on the pressure. The concentration of the species. Sorry. I should have a parentheses here and here, yeah. And then we have, I'm going to run out of space. So this part is the same as what we had before. The progress of the reaction, progress variable is dependent on the forward rate, rate constant K, and then the concentration of the species raised to the stoichiometric coefficient minus the reverse rates times the concentration of species raised to the stoichiometric coefficients in the reverse direction. But we add a term here in the beginning, This is just saying that this reaction, this reaction, Q of I, the progress of reaction can be dependent on the concentration of species, total concentration of species, times some term AKI, and this is a factor that says how much species concentration are dependent on this, how much they contribute to the three-body reaction. So how much a species contributes to or as a third body. We call this a third body collision efficiency, And this term M, is simply the sum of all the concentrations of species. Okay, so what this says, all saying is, sometimes in a reaction equation, you'll see something like this, H plus O2 plus M. In a reaction mechanism, it goes to HO2 plus M. The code then says, okay, this reaction, the rate, or the progress of the reaction is dependent on the kinetic parameters, but it's also dependent on some overall pressure, which is based, which is, of course, the concentration of species is related to the pressure. But sometimes some species contribute less or more to this overall M term. And how that's done is you add this factor, and sometimes what you'll say, if there's no A provided, it will just assume it's 1. Yeah, so the contribution of any reaction or any species as a third body collider is 1. But sometimes you'll see in reaction mechanisms, they write H2O. So below the reaction, they'll write a species, H2O, and they'll put a number 2 next to it. And they'll put argon, and they'll say 1.5. Yeah? That tells the code then that AKI, the contributor, now you treat water vapor, or H2O, as a double, 2 times. You take its concentration, you multiply its 2, so it contributes 2 times as much to the overall pressure dependence of the reaction. So it's just and how do they know, okay, which species are contributing more as a function of pressure to a specific reaction? Well, one way is people do experiments. They do experiments in argon, in nitrogen, in water, and they noticed, okay, there's slight differences in the ignition limits for hydrogen. Well, why are there differences in the ignition limit if you change the bath gas? Yeah, if everything is pressure independent and everything is only a function of temperature, the bath gas shouldn't make a difference. Well, if you change the bath gas and you change the pressure, those explosion diagrams change. So one way is just experimentally then, they say they figured out if you put water in, somehow the third limit comes down lower, the third branch. And that's because at lower pressure, water provides more, you could say, intensity to this overall pressure-dependent reaction, which allows it to happen faster. So like this, it can happen experimentally. Also, you could do it with quantum chemistry, so people do quantum chemical calculations and molecular dynamic calculations, and they calculate, again, in a bath gas, as they change the bath gas, they see a simple reaction, how the kinetics can change, and they try to determine what these factors are. I'm not an expert in this. There's a professor in Columbia, Michael Burke, okay? He studies this. This is one of his main contributions, is how you determine, these factors, the pressure-dependent factors based on the different colliders that are there in the bath gas. Okay, so, but there's other ways to express. This is the most basic way. I show you here is the most basic way to express a pressure-dependent reaction. You just say that in the code that the overall progress of variable of this reaction is a function of total pressure. But there's other ways to do it. You can even write a reaction in a pressure-dependent form. So as we said here, we could have unimolecular fall-off reactions and chemically activated bimolecular reactions. So the first example is for unimolecular reaction. Now, let's say we have, for example, this reaction. This is a unimolecular reaction in the reverse direction. Ethane, C2H6, can react to form methyl radicals, CC bond scission. And it's been found that this reaction, as you change the pressure of the system, the rate is different, okay? So, and there's different ways you can, to observe this reaction. You could do this reaction, C2H6 going to CH3 plus CH3, again, in a shock tube. You can dissociate ethane, and you can observe the formation of methyl radicals. Groups like at NIST, at Stanford, have done these types of reactions, and they vary the pressure in the reaction, and then at a fixed temperature, they see a change in decay, the rate constant. And they find that at high pressures, you have one rate, but then as you go to low pressure, you have a so-called fall-off regime, that the rate starts to slow down, okay? So in the low pressure limit, the third body collision is required to provide the energy for this reaction. As you go to high pressure, there's enough third bodies or enough colliders around which allow the rate to accelerate and be fast. So you kind of have two limits of this rate, one at the low pressure and one at the high pressure. Give me the laser pointer here. So the one at the low pressure, you have a low pressure limit and you have a high pressure limit. And now we need to fit this pressure dependence in different ways. So like we fit temperature dependence with the Arrhenius law, there's different ways to fit these observed pressure dependences in K. So this has nothing to do with now, in this reaction here, the K does not change, okay? Ks are fixed, the rate constants are fixed. This is not a pressure dependent in the sense that the rate constant is pressure dependent. Here the progress of the reaction is pressure dependent because the Ks are fixed at pressure. All that's changing is the progress of reaction based on the overall pressure of the system, which is based on the concentration. So that is pressure dependent, but it's not the rate constant which is pressure dependent. It's the overall rate of progress of reaction which is pressure dependent. But in this case, we're saying the rate constant K, as we see here on the y-axis, is a function of pressure on the x-axis. Okay, so how do we deal with this? So this fall-off reaction, we say this fall-off reaction has one limit, one rate, that is first order with the total concentration of species or pressure at low pressure, like a three-body reaction. But as the pressure increases to a very high pressure, it becomes zero order with respect to M. And so any type of dissociation reaction, like we saw previously, C2H6 going to two methyl radicals, gives us this, this form of expression. So if you were to look at K in this chart, this is graphically how it's explained. In the equation form, K is a function of temperature and it's a function of total concentration of species or pressure. And it's equal to K naught times M. K naught is the low pressure limit of the reaction, the low pressure rate constant, and then divided by 1 plus K naught over K infinity being the high pressure limit for the rate constant, so and times M. So if you look at this expression in the low pressure limit, this K naught M, in the low pressure limit, yeah, this K naught M approaches simply K naught, the denominator becomes just 1, and in the high pressure limit, this equation will approach K infinity. And you can write this in a different form, rather than writing K naught M over 1 plus K naught M over K infinity, you can just say a term we call the reduced pressure, PR. So PR is now equal to K naught M over K infinity, essentially this denominator term. And then you get the rate constant is now Kf is K infinity times PR, the reduced pressure, over 1 plus PR. And now we have to find out what is this reduced pressure and what is this K infinity and so on, so we can fit it. So there's two different ways to do it. One is called the Lindemann function. The other is the Tro expression. So first, let's look at the Tro formalism. So how, you could simply, this is the Lindemann function. Again, Kf is function of temperature and reduced pressure, K infinity times PR over 1 plus PR. And this, again, as we say, is a function of temperature and reduced pressure. And the Tro formalism is, Tro is a German kineticist, still active today, okay? He presents how you can write this rate expression in a way that you could put it inside of a code, okay? So he says K is K infinity, the reduced pressure over 1 plus the reduced pressure times some function F, and then he has a very complicated expression for F, yeah? It's shown here. I won't read it all out, but it's just an equation, okay? It's just a fitting function that came to work. There's no theoretical foundation for this specific function, but it's a function that tells us how F can vary with the reduced pressure. You see here there's some constant C. C is some constants here times log times F center. There's another variable N. There's another variable D, and then there's this term F cent. F cent has a complex dependence on temperature, and I'll show you what this is. So it has some alpha term, and then it's a function of temperature T triple star, T star, T double star, and so on. And in the end, in your mechanism, what you will typically find is something like this. You'll have a reaction written as methyl plus M goes to form C2H6 plus M. This is the high pressure rate limit, it's saying. So it gives you K infinity. K infinity is 2, 10 to the 15, some temperature dependence and some activation energy. It gives you the low pressure limit, K naught. So those are two things we need, right? We need K naught and K infinity to get the reduced pressure. Those are given in the model. And then you have these fitting formulations. So we have A, or alpha, which was shown in the previous slide, 1 minus alpha. You're given T triple star, 570, T star, 1 times 10 to the 30. So these are not physical numbers, right? It's not like it's a temperature. It's just a fitting function, okay? And then T double star is 1 times 10 to the 30. All of this goes into this equation, and you can get F cent, and then you go back and you look at, you can calculate the F here based on F center, and you can calculate the K at different pressures. So again, just all of fitting formulation. You see here at the bottom, they've also denoted those so-called activities, what did I call it before? The factor that says how much species contributes to a third body, that's shown here. So in this reaction, they say water contributes 5 times as much. CO, 2 times as much. CO2 is 3 times as much. And then if there's nothing there, it means everything else is 1. Yeah? But anytime you have these 3 species, modify the the progress of reaction accordingly. So what does this do for us? Well, here you can see now pressure-dependent rate at 1,000 K, again, for this reaction. So we come back to this thing. At low pressures, if you look at this formalism, at low pressures, K naught, M approaches 0, right? At low pressure, this term M has to approach 0. And if this approaches 0, then the K essentially becomes K naught in this expression. So your initial low pressure rate constant. And if you're at a high pressure, this K naught M, this M becomes very big. And if this M becomes very big, then your term here, PR over 1 plus PR, essentially approaches to 1. And then you will get K infinity. And then you get these 2 limits. And then how you fit in between those 2 limits is based on this F term, which I showed previously, has some complex dependence depending on how you fit it. So you'll find these types of reactions. When do they really matter? Well, it's a good question. Okay, in combustion, most of the time we're operating above 1 atmosphere, sometimes 10 atmospheres, 100 atmospheres. Typical IC engine, you might inject your fuel around, in a diesel engine, in-cylinder pressure at injection might be around 10 to 20 bar. And then after combustion, it goes to 200 bar. Gas turbines are operating around 40 bar. SI engine, when you're firing the spark, you're already about, above 8 to 10 bar. So, and most of these fall-off reactions are happening at subatmospheric pressure. So typically once you reach like 5 bar, 10 bar, most of the things have reached their high pressure limit. All this very nice, eloquent pressure dependence really happens at very low pressures. So I'll show you later on in the course, sometimes we can neglect pressure dependence for some reactions if we want to predict things related to engines, because it doesn't happen, they're already at high pressures. You're nearing the high pressure limit, so you don't need to really consider all these fall-off aspects. But if you're simulating things and people do experiments in low pressure premixed flames, and those experiments are done at like half an atmosphere or a quarter of an atmosphere, then they have to include these types of reactions. So it all depends, again, how complicated and what type of systems you're actually trying to predict. But from a theoretical perspective, we know they exist. And again, if you want to be correct from theory, you should include these types of pressure dependencies. Now, the other type of pressure dependency is what we call a chemically activated bimolecular reaction. So that same reactants we saw previously, CH3 plus CH3 can react to form ethane, or reverse ethane decomposes to form methyl radicals. Okay, this is a three-body reaction which goes CH3 plus CH3 down into a well, C2H6. And the dissociation goes back up to CH3 plus CH3. In addition, ethane could decompose by losing a hydrogen to C2H5 plus H. Now, a chemically activated bimolecular reaction is one that skips the well in the middle. So in this case, CH3 plus CH3 can skip over this well and go directly to C2H5 and H. Yeah. And you wonder how this happens. Well, this has got a well-skipping reaction because you don't need to go through that so-called well. Yeah. So CH3 now this appears to be not an elementary reaction. CH3 and CH3 looks like you need to form a bond together to form C2H5, and then the H has to leave. But it happens as a single it can happen as a single step. I mean, initially CH3 plus CH3 in the main reaction will form the well, C2H6, and then hydrogen will be lost to form the products to form C2H5 plus H. But it has been known, I mean, again, through theoretical calculations, that this can be a well-skipping reaction. So CH3 plus CH3 can form a transition state. In this case, we call it an activated complex, C2H6. And that complex has enough energy that it quickly dissociates to C2H5. So it's not a stable molecule. So that activated complex is a transition state. It looks like ethane, C2H6, but it's very high energy. It's so high energy that it never drops down into the well and forms a stable C2H6. It stays as high energy and dissociates to the products. So we call this chemically activated. This means that the reactants, once they collide and react, they form a transition state that's so active that it can immediately go to products. So hence chemically activated reaction. Or another way to call it well-skipping reaction. So it skips the well. Now, these types of reactions are favored at high pressure. So it's the opposite. They're favored at low pressure, and they're disfavored at high pressure. And why is this the case? Well, at high pressure, CH3 and CH3, when they hit each other, they'll also be hitting the bat gases. And these bat gas molecules, they'll collide with this activated complex, and they'll take the energy away from it and allow it to fall into the well. So at higher pressure, as the pressure increases, this activated complex cannot be formed, and you drop down into the well. So this main reaction is disfavored. So the rate becomes slower as you go to high pressures. And at low pressures, well, there's not enough bat gas molecules around to take away energy from the activated complex, so it can be formed and it can dissociate. So this type of pressure-dependent reaction has the opposite form as the previous one. Previously, we saw low pressure, low rate, high pressure, high rate. Chemically activated is the opposite. Low pressure, high rate. High pressure, you have a low rate. And again, you can fit them with the same equation, K naught. Now instead of K infinity, you put K naught, okay? So the rate before we had K infinity because K infinity is the high pressure limit. Here now we have K naught, the low pressure limit, and then you still have 1 over 1 plus PR. Okay, so that's just the difference. Two types of pressure-dependent reactions. You'll see them in mechanisms. Unless you're in the field of kinetics and very detailed types of kinetics we're developing, you'll be concerned with these things. But if you're just using mechanisms, you should understand when you see these things in codes, why they're there and what it looks like. And again, you can fit this with the same troll formalism, or they have different fitting ways of doing it. The nicest way to fit now, in most modern mechanisms, we just use a simple P-log formulation. So when Troll was making his formalism, those complex fitting functions, everybody did everything using polynomials. I mean, all he had was a basic polynomial expression, because polynomials were the easiest thing to calculate in the computer, because the amount of memory was limited. And so you just have a polynomial equation and you calculate on the fly. Now we have a lot more memory in the computers, so now we just put it as a table. Because tables, they take up space in memory, but who cares? We have enough memory. So now this is a very nice way. I think it actually, Professor Zhu here at Princeton came up with this idea, because it was really complicated to look at these troll formalisms, and then if you make a mistake in your code, you get the wrong answer. So now we just plot them as a table. We call it a p-log formulation. The rate is a function of the logarithmic of the pressure. And simply you write your equation, and then you just write the Arrhenius parameters at every pressure. So at pressure of 0.01 atmospheres, this is the Arrhenius parameters. At pressure of 0.1, these are the Arrhenius parameters. At 1 bar p-log, you'll have these Arrhenius parameters. So you're just providing a different k at different pressures. And that's all this is, right? This is k at different pressures. And you provide this table, and then the ln of any pressure is simply ln of ki, sum of one of the known pressures over, and then you interpolate between ln ki plus 1 and I, and based on the difference in pressures, and then you can look here, you'll get a simple interpolation between two curves. So it's a simple way to do it, and you typically have it like this in increments of just tenths, so 0.1, 1, 10, 100. It's not perfect, okay? You might have some errors, but again, in combustion simulations, the dependence on pressure is not so large, again, between 1 and 100 bar that you need to worry so much if you interpolate. So this is something you'll see now in most mechanisms today. You won't find, if you still see those troll formalisms, it means somebody wrote that reaction like 30 years ago, and we just keep it there because it's been there. But nowadays, most people in papers, they'll always publish now using these logarithmic formulations. It's much easier to deal with. All right, so that's it for today. Yeah, exactly 12:15. Now we have to go take the picture, and the picture is going to be over in the chemistry building where we had the barbecue on Sunday. So see you guys there.